what we did so far. So we are working in category O, which means that G is a semi-simple complex Lie algebra finite dimensional. This theory has an immediate generalization to symmetrizable Kac-Moody algebras outside the critical level. That is that's important. So we have this triangular decomposition, Cartan and Borel, and then this gives us, for any linear form on the Cartan, gives us three objects. So first there is L lambda. This is simple. Then there is simple with highest weight lambda. This is the Wörmer module, and this is the projective cover. In O. So the original Cauchy-Lustick conjecture which is really the most, the first version of a series of Cauchy-Lustick type conjectures, states that the character of L W dot lambda is given as a sum over X in the Y group. Then there's a sign. Then there's multiplicity. I think that should be like this. Evaluated at 1, and then here's the character of the Wörmer module at the parameter x dot lambda, and here lambda is antidominant and regular. Antidominant, integral, and regular. Okay, this was the original conjecture, and the equivalent conjecture is the following multiplicity conjecture. So you can rewrite this in multiplicities of Jordan-Hölder decomposition series of Wörmer modules, and it says that delta, say x dot lambda, L W dot lambda is given by the Cauchy-Lustick polynomial at parameters x and right. Oh. Right. Yes. Okay. Let me write down the history of these conjectures. So those were proved by Beininson-Bernstein and Brzezinski-Kashiwara independently using the same ideas. At the moment I don't know when this was proven. 82. Mixed sheets on the flag variety. So now there's a new. So this theorem is a very hard theorem in geometry. So the proof is extremely difficult. And there is a new proof of the decomposition theorem. So that it was first proven by Beininson-Drinfeld, Deligne, and Beininson-Bernstein, Deligne, Beininson-Bernstein, Deligne, and Gabber. So, and then Saito found a different proof, and then Migliorini and Di Cataldo came up with a new proof of this, which didn't use characteristic P methods in 2005. So they used a very, very intricate inductive argument using Hodge theory on complex varieties. That was the first time when I myself thought, okay, there's a chance to understand the proof. So it's kind of still very, very difficult, but it stays in complex geometry and uses Hodge theory and Riemann-Hilbert relations and so on. And Jordi Williamson and Ben Elias, in a sense, kind of translated the Migliorini-De Cataldo proof into Zergel bimodule language. But if I just say they translated it, I'm not giving them enough credit. I mean, it's really an ingenious translation. So that is Elias and Williamson. So they give a direct proof of the decomposition theorem in Zergel bimodule for Zergel bimodules. And they are highly inspired by Migliorini, De Cataldo Migliorini. So that was in 2007. Oh no, sorry, I'm wrong again. That was 2011. 2012 maybe. 2012. Well, the very interesting aspect of this proof is that it also works for arbitrary Coxeter systems. So, for example, you can write down Castanussic combinatorics for an arbitrary Coxeter system. We'll come to that. I define that, and you find polynomials like those polynomials, and you see once you prove this conjecture, there's a kind of a trivial statement that you conclude, namely that, I mean, this number is positive or non-negative, right? Multiplicities are always bigger or equal to 0. And this actually holds for each coefficient of this polynomial. And that was an open question for arbitrary Coxeter systems. The proof of Elias and Williamson settles this question too, because it's just it works for arbitrary Coxeter systems. So,
Does it prove the original decomposition theorem at all? Original version, or is it only strictly in this bimodule?
It proves the decomposition theorem for flag varieties. In the case of flag, well, the decomposition theorem is a statement about a proper map between complex algebraic varieties. And in case this is the map, say, from a Bott-Samuelson variety to a flag variety, or from a flag variety to a partial flag variety, let me think, yeah. In these cases, Elias and Williamson give a proof for those maps, but not in general. So let me just, yeah.
So this is the character formula. What about the Williamson-Wilson proof of Jansen's conjecture? Do we have a PPD-free proof of that?
Yes. Actually, that is a very good question. Yes, we have now a geometric free proof of that. But that follows kind of a different line of argument. So first, Zergel translated this. So Zergel translated the original Janssen conjecture. He tried to translate the original Janssen conjecture into a conjecture about Zergel bimodules. Kind of. While he was doing that, he realized that he couldn't find the Janssen filtration on bimodules, but the so-called Anderson filtration, which is a very similar filtration. And then one of my PhD students, actually, in a diploma thesis, proved that these two problems are equivalent using moment graph language. And so Zörgel and my PhD student Johannes Kübel, they then showed that you can translate Janssen's conjecture in a bimodule, Zörgel bimodule language. And then you can use a local version of Elias-Williamson's proof to settle this. This local version is not yet written down, but I mean we kind of have all the details for Janssen's conjecture too. So now let me just state the linkage principle and not prove it here to save some time. So this says the following. So define an equivalence relation denoted by this tilde on the dual of the Cartan by the following. Lambda is equivalent to mu if and only if lambda is in the orbit of a certain subgroup of the Weyl group, or the orbit of mu, where W mu is the group generated by our reflections as alpha, where alpha is a positive root, and mu, alpha check, is an integer. So this is also called the integral subgroup. Okay. So why is that called linkage principle? So it follows from this that category O splits into a direct, let's say, direct sum of subcategories O mu, where mu, so O mu bar, where mu bar is an equivalence class, and O mu bar is the subcategory of all objects in O that have the property that if L nu is a subquotient of M, so that means the Jordan-Hölder multiplicity is non-zero, then nu is in mu bar in this equivalence class. So this kind of follows from here. You see we have projective covers. So every module has a projective. I mean, there are enough projectives in category O, and then we look which projectives admit non-zero homomorphisms, and they certainly should be in the same block. And so this gives a block decomposition of category O. So there's no non-trivial homomorphism between objects in different blocks, because each homomorphism can be kind of generated by morphisms between projectives. So there's a theorem, Benson-Bernstein, uses the reciprocity and well, the Shapovalov form and Janssen filtrations, and there's a lot. So I should probably, if I'm very honest, I should add other authors there. But yeah, those are the indecomposable. Oh, those are, yes, all mu bar is indecomposable.
So when you, in that definition, maybe you should add M, indecomposable?
Oh no, M might be, no, I mean, an object here might, in this category might be decomposable. But this block as a whole is indecomposable.
No, but then if you put that, because you could add...
So M might be decomposable, but in each direct summand, each simple subquotient might be should be in this equivalence class. Okay, so this is the linkage principle, and it very well fits this description, because you see here, this in particular says that the only subquotients in the Römer module have highest weight in the same orbit. That's kind of reflected in this block decomposition. So now we study Janssen's translation functors on category O, and I have to say so far everything makes perfect sense with analogous statements in the modular case. So now there's translation functors. Okay. So, right. Now on the right side, let me now start with introducing the Hecke algebra and the Castellan-Lustig polynomials. And then we'll see in a second why everything, why these Castellan-Lustig conjectures actually make sense or are reasonable. Or, I mean, you see the real meaning of the conjecture in a second. So the Hecke algebra. So the Hecke algebra is associated to a Coxeter system. In our case, it's the Weil group with generating set the simple refractions. So what do we do to get an algebra? So first we define L, which are Laurent polynomials over the integers. It's just this ring, the ring of Laurent polynomials in one variable. So as a space, the Hecke algebra H is a direct sum over all W in W, L, T, TW. It's just a free L module generated by elements of the Weil group, and the multiplication is given as follows: Tx times Ty. So the it will be an L algebra. So the multiplication should be L bilinear. So I only have to say what the product is, and this is Txy. Well, so far so boring. Only under the condition that the length of xy equals the length of x plus the length of y. So this is a trivial. What do you say? I mean, trivial and obvious. I mean, an easy to state relation. But if you, for example, if you take a simple reflection, then you have s squared equals the identity. So this is not satisfied. So Ts squared equals, let me just look it up, v to the minus 2 t at the identity element plus v to the minus 2 minus 1 ts. So these are the two relations in the Hecke algebra. So it's not clear that this actually defines a multiplication, and of course writing it down is easy. But I should at least tell you where it comes from. This is if you look at the corresponding group over a finite field of Q elements, then you can look at biinvariant functions. So B is the Borel upper triangular matrices with entries in FQ for the case GLN FQ, and you look at biinvariant functions. This is a finite dimensional. So functions on this space. So this is finite dimensional with say Z coefficients. Functions on this space. This is a free Z module with basis. Well, the delta functions on this this is a discrete set. The delta functions on this set, and turns out this is identified with the Weil group, and this space comes with a convolution product. So because it's bi-invariant functions, you can convolve bi-invariant functions. Now, if you sit down and calculate the convolution of two delta functions here, you see Q appearing polynomially. You can, I mean, it's a very funny exercise to do it for GL2 or so. You see Q appearing polynomially, and if you take a square root of Q and call it V, you get kind of these relations. So the Hecke algebra is what it, I mean, it's defined as functions on this double quotient under convolution, and if you take a square root of Q and consider it as a parameter, you arrive at these kind of relations. So that's where it comes from. So that was that is an older story, and now Kashtan and Lustig came, and they defined a new self-dual basis. So self-dual with respect to the following involution. So you can define D, an involution on this algebra. You just it's defined. You just define it as follows. So D of the parameter V is just V to the minus 1, and D of Tx should be Tx minus 1 minus 1. So it turns out that all these Tx's are invertible in this algebra. And this you use to define the involution. And so instead of, so yeah, the theorem is the following. There exist unique elements. Let's call them H, W underline, because there's a slightly different normation. HW underline in the Hecke algebra with the following properties. So first, they are self-dual. So if you apply D to this element, you obtain it. So it's stabilized by the involution, and H underline W is an element in the following subset of the Hecke algebra. So it starts with HW. So I should maybe, sorry for all the notation, HW I defined following circle, V to the V to the length of W, TW. So this saves some notation to go to this basis. So plus a sum over all x smaller than W, and then some polynomials, and these are the Kashtan-Lustig polynomials, times hx. And this turns out that these polynomials, so that's not an element, so this is equal to this. Let's say the following. So hxw is a polynomial in V. So no V to the minus 1 occurs, and hxw evaluated at 0 is 0. So there's no constant term. So those are the polynomials appearing in the conjecture. So, but why? So what? I mean, now let's. let's step one step back and just try to understand why there should be any connection. Well, in the translation I gave you so far, it's not yet clear what this duality would mean for the projectives, because these projective objects are not self-dual for the duality in category O. And also this does not make much sense yet. But now the connection is as follows. So we can construct H bar W inductively. So H underline S is TE plus VTS. So this is checked directly. You just have to make sure that it's self-dual. I mean, the second property is easy to check, right? It starts with oh, sorry, I got it. So here, the V should be in front of TE. It's TS. Sorry. Right. So it's V HE plus HS. Okay, sorry. Yeah. So that should be correct. Better check if I.
This is S times TS, right?
Yeah, exactly. TS is. Yeah, okay, yeah. Okay. It's a direct calculation. Okay, so now if H underline W is already constructed, and induction goes on the length of W, for example, or on W in the Brüher order. So if HW underline W is already constructed for all W smaller than Y, and suppose that YS is smaller than Y, then you do the following. So because YS is smaller than Y, H underline YS is constructed, and now apply, just use the multiplication with HWS. So this involution is an algebra involution, so it commutes with multiplication. So what we have here is self-dual. And so let us write it in terms of, so say Bx, in terms of this Hx. And the multiplication, it kind of makes sure that the x's that appear are smaller or equal to y. I mean, we'll see that in a moment why this is the case. So of course it can be written as in this form, and the inductive. So maybe I should give you another formula. You can check directly that if you multiply Hs from the right on one of these basis elements Hx, you get the following. So you get Hx plus VHXS if x if xs is smaller than x, and you get HXS plus VHX if x is smaller than xs. This follows very easily from the defining relations of the Hecke algebra. For example, if I didn't do any mistake, this is certainly true when you put x equal to e. HE is the identity element. And then you're here in the second line, and you get this this relation back. And you see what you get by right multiplication is only something that has an x and has an xs. Well, wait a second. I think here we have a v to the minus 1. Sorry. Here we have a v to the minus 1. That makes the whole algorithm interesting. So now, since these polynomials, the coefficients of these self-dual elements, the zeroth coefficient is 0. So here the zeroth coefficient is 1. And the coefficient of degree 0 of these polynomials is 0 anyways. So the only, you only get for some instances here a v to the minus 1, right? But since all the coefficients start with a v instead of, apart from the first, you can show that this is, can be written as hxs, hy plus some, for all x smaller than y, some bx, hx, and these are now still honest polynomials, but they might have, so evaluated at 0, they might be non-zero, because there might be some v to the minus 1 coming into play. So, and now I claim that hy underline is constructed as follows. You take this this product ys times hs, and you subtract the following sum: x smaller than y, b, x. You evaluate this at 0, and subtract the corresponding h underline x. So now I claim this satisfies these two relations. First, it is still self-dual because this is self-dual and this is self-dual. I mean, this is just a number. So this is a self-dual element. And so the only reason why this is not the same as h underline y is that here might be some polynomials which has a non-vanishing constant term. But these constant terms are just subtracted in this sum. What is not clear here is that what the coefficients in this sum are. I mean, you're subtracting something, right? So you could end up with some non-zero coefficients. So this is, well, it's kind of easy to show that this satisfies these two relations. The theorem says it's unique, so this is the self-dual element. So you see, now you write this, you can write this as hys plus, and then here you have the hy plus x smaller than y, x y hx. You can write it in this form, and it's not clear that these polynomials have non-zero coefficients. Non-negative coefficients. Okay, so representation theoretically, we are closing the theory more and more. So okay, this is the algorithm. We'll need it in a second again. But now we talk again about representation theory. So we can define, say, how should we I call it h of p lambda. This should just be a formal sum. Say h. We are in the principal block still. Say hy dot 0. We are only considering the principal block for simplicity. This will be a sum over elements of the Y group, and then we'll have some e to the x. This will be an element in the group ring of the Y group, and the multiplicity here. Let's just put py dot 0 delta x dot 0 e to the x. Okay, I mean this is just a definition of h y dot 0, and now we can translate the Cauchy-Lustig conjecture one more time into the following. So the conjecture, I mean this is a kind of very stupid, naive translation. It would say that if we take this, so this sum is given by the self-dual element at y evaluated at 1. So what does that mean? So evaluation at 1 should give a map from the Hecke algebra to ZW. I mean, you evaluate each coefficient, which is a polynomial in v and v to the minus 1. You evaluate this at 1. And this just means, this relation just means that this coefficient is the corresponding Cauchy-Lustig polynomial evaluated at 1. Okay, so now translation functors. Right. So you see here, right multiplication with this h underline s transforms hx into something involving x and xs. But we have seen that before. We have seen that the translation functor theta s evaluated at delta x gives a module with has a Wörmer flag where delta x and delta xs are appearing. So these hx should correspond to Wörmer modules. And these h underline x should correspond to projectives. So now so if we apply theta s to a projective px dot 0, we know this is projective. So it will split into indecomposable projective covers. And it's easy to see that px dot xs dot 0 appears once, because the Wörmer module delta x dot 0 appears once here, and then that's the only one where you apply theta s that can give a contribution of xs dot 0, given that x is smaller than xs. Projectives we have to subtract in order to get the one we want. The Cauchy-Lustig conjecture gives us numbers. Here we have this kind of translation functor applied to the object. We get what we want plus something that we have to subtract. And the multiplicities should be the same. And the problem now is that in an algebra you can very easily write minus some elements, right? But in representation theory we have to show that these occur as a direct summand, so that we can subtract them. And this is the tough part. This is the decomposition theorem tells you that this decomposes as it should. Okay, so okay. Now, I mean, you can sit down and try to prove it directly. One of the first obstacles here in this theory is that these polynomials only make sense once you have a grading, once you can play around with a v to the -1 and the v. I mean, you cannot construct these numbers directly without first going to a ring of Laurent polynomials. They don't make sense. I mean, the casualistic algorithm that I outlined here doesn't make sense over the integers. You need Laurent polynomials. And here's absolutely invisible what v means. V adds an extra grading on all these objects, but not directly. I mean, from a representation theoretic viewpoint, this v is completely invisible. Okay, so we have to translate it into something. And now I think I haven't looked at the clock, but I think that's a good time to stop. Yeah, tease there. I'm sorry, I a little bit too long. Okay, let's pause for a while.